Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to learn about and implement depth-first search. Depth-first search is a way to traverse graphs or iterate through a graph's nodes. And what it does is it iterates down a path fully and reaches the end of that path before moving on to the neighbors of a node in the same level. So it goes deep into a path before it goes wide into the graph. This is in contrast to breadth-first search that goes wide before it goes deep. We have our starting node of 0, then we go to 1, 4, 5, 8, and then 7. So this was a full path. Because it's an undirected graph, we walked all the way down this path from 0 to 7 before moving on to the neighbor of 1, which is 2. And this is the fundamental concept of depth-first search, going through paths before going wide. And trees are just a special form of a graph. So you can use depth-first search on a tree just like you would on a graph. It just travels down branches before going wide into a level. Another way to think about depth-first search is like a maze. You start and then you have a choice. Well, you wouldn't go check one spot left, one spot down, then one spot right. You would go all the way down a path to see if it works and then come backwards if it didn't. So you traverse these full paths in any direction that you can before checking the other options. So let's discuss the fundamentals of depth-first search. The key detail is to use a stack when you implement it. This means we're going to be iterating in a LIFO manner. So the last one added is going to be the first one used. This is how we go deep into the graph instead of going wide. And this stack can either be the recursive call stack or an actual stack data structure you use in your code. Depth-first search goes deep before it goes wide, so we just follow a path to its end. And then you always want to track the nodes that you visit because this ensures that you won't visit the same node multiple times or get caught in a cycle where you go around in a loop. So let's really understand why we use a stack and what this data structure provides us for depth-first search. So you start here at the root node. You add it to your stack. Then the root node has 3 neighbors, so we push neighbor 1, neighbor 2, and neighbor 3 to this stack. Then we pop the top neighbor off the stack. Now we're visiting neighbor 3. Well, neighbor 3 has 2 additional neighbors. So we add deeper 1 and deeper 2, that's what we're calling this node's neighbors, to the stack. Then we're done with neighbor 3, and then we pop deep 2 off. Now we add deep 2's neighbor, deep 1, and deep 2. So you can see, because we're using a stack, these deeper nodes are going to be higher up and therefore visited first. So we won't visit neighbor 2 until we get all the way through with all these deeper, more nested graph nodes. So now that we've seen how the stack works, let's really walk through a depth-first search, see how we traverse nodes, see when we push them to the stack, then how we pop them and use them, and then also how we set a node as visited. So we use a set data structure, and we add a node to this set once we account for it in the traversal. And with a set, any item can only exist once. So if we see the item exists in the set, we won't visit it again. And here we're starting at the root, and graphs don't actually have root nodes. You can start at any node, but I'm just calling it the root to indicate it's the first node that we're going to visit. So we start at the root, we push the root to the stack, and then we also set the root as visited since it's accounted for in the traversal. Then we pop the root, and we add its 3 neighbors to the stack, N1, N2, and N3. And then because we've accounted for them, we add them to the visited node set as well. So we added N1, N2, and N3 to the stack and the visited nodes. Then N3 is at the top of the stack, so we pop N3. Then we add N3's neighbors, D1 and D2, and we also see the root as a neighbor. But because the root exists in the visited node set, we don't go through it again, so we don't add it to the stack again. Then because D2 is at the top of the stack, we pop D2. Then we add D2's neighbors, DD1 and DD2, but then also N3 is a neighbor, but because N3 exists in this visited node set, we don't add it again. Then we pop DD2. And there's no more nodes to add, they've actually all been added. So now all the items on the stack will just pop off to move backwards. But we see that once we reach DD2, we've actually gone the full length of one of the paths. And we did this by using this LIFO functionality of a stack. Because the last one you add each time is the first one you use, when you push these items, you continue to go deeper and deeper. Then as you pop them, you get back to these earlier items, the oldest ones you added, and then you go down their paths. And then we saw the first 3 items, N1, N2, and N3. For N1 and N2, they won't be visited until you pop off all the items that are on top of them in the stack. So that's how we visited all of N3's paths before moving on to N2 and N1. So let's move back to the DD2 node. We popped it, and then DD1 remained. We visit that and pop it. Then we get D1, pop it, and then finally we're at N2. We pop N2, use it. It doesn't have any neighbors other than the root, which has already been visited, so we're done with that path. We pop N2, and then finally we get back to N1, which is the last node we visit. So we pop N1, use that, and we're done. So with depth first search, we went deep by pushing items to the stack and using the most recent one that was added, which allowed us to continue to go deeper and deeper down a path until you reached a node at the end that didn't have any neighbors, or the neighbors that it did have had already been visited and set in this visited node set. So that's the key element of depth first search. Use a stack and its LIFO order to go deep, and then set visited nodes so you don't go through nodes more than once. An example of an issue with this is where we have this N3, D2, and D1. If you don't add them to the visited node set, each time you visit a node, you'll push the other 2 and then continue to just go around in a circle. Now let's discuss the pros and cons of depth first search. The primary pro is that it's assumed to typically take less memory. Graphs typically get wider than they are deep, so you're going to store less nodes when you go deep first. Depth first search is always a good choice when you want to determine if a path exists. So if you're going from a starting node to an ending node, if you follow paths to their end, you will reach this termination point quicker than if you checked all the neighbor nodes first, which would happen with breadth first search. Then the con is if your graph does get deep, if this assumption breaks that it is wider than it is deep, then your algorithm will actually slow down and not be the best choice. So before we implement depth first search, let's first just quickly run through the logic. The fundamental data structure used in depth first search is a stack. So we initialize that, and then we take our starting node and add it to the stack. We also need to track the nodes we visit, so we use a set data structure and then add our first node to it since we've accounted for it in the stack. Now we iterate through the nodes. We can either use a while loop and then iterate as long as we have items in the stack, and we use a while loop because we don't know how large our graph is. We don't have a length property, so we just have to iterate as long as nodes exist. Or you can start recursion. You recursively walk through each node and its neighbors until there are no more nodes that can be visited. Once you start your traversal, you remove the top node from the stack. Then you call your visit function, or however you want to use it within your algorithm. You add this node's children or its neighbors to the stack. You also set these nodes as visited because they've been accounted for in the stack. Then you just continue to repeat this. You use your while loop or your recursion until you run out of nodes. And now we're ready to implement depth first search. We're going to use a standard graph node that has a data property, and it also has edges, which is going to be an array of other nodes that it's connected to. When we visit the node, we're just going to print the data of that node. So we're going to write a depth first search function that takes a starting graph node as its parameter. Our implementation for depth first search is going to be iterative, but if you want to see the recursive solution, it should be at the bottom of the article you're reading. The key data structure in depth first search is a stack. This is where we're going to store the nodes that we need to visit. So we initialize our depth first search stack, and we're just going to implement it using a dynamic array. We also need to track the nodes we visit. This ensures we don't visit the same node twice, and also prevents us from getting in a cycle. We'll also add our starting node to the stack, and also, since we've accounted for it in the stack, we'll add it to our visited nodes. Since we're doing this iteratively, we're going to use a while loop, and our while loop iterates as long as we have items in the stack. This means we have nodes that we still need to visit. Then, at each iteration of the loop, we pop off the top item. We'll visit the node. And now we need to add this node's edges to the stack. But we only add this node to the stack if it hasn't already been visited. So we check if visited nodes has the child node. If not, we push it to our depth first search stack. And since we've accounted for it in the stack, we add it to our set data structure. And that's it. That's the logic of depth first search. Let's check it out in this example. And the way I've set this up, it will print the nodes in order by going deep first. So let's just quickly visualize this example before we run it. Our starting node is node 0. So we initialize a new graph node with the value 0 and set it to the starting node. Then we set this node's neighbors, or its edges. We have 6, 4, and 1. So we added the nodes 6, 4, and 1 to the graph. Then we take the edges at the second index, which is graph node 1, and then push a graph node with the value 2 as an edge to that. Then for graph node 2, which is edges of the 2 points to 1, then edges of the 0 points to this node with the value 2, we push the graph node with the value 3. Then finally, edges of the index 1 for the starting node is graph node 4, and we push graph node 5. So here we added that edge. Then when we perform depth first search, we start at 0, add its neighbors, and then we visit it. We push 6, 4, and 1 to the stack, and then we pop node number 1. We visit number 1, and push number 2 to the stack. We pop 2, visit this node, and then push 3 to the stack. Then we pop 3, and now we return to the node that was next in the list. We've gone depth first search, or fully visited this path. Then we can move to the next neighbor. 4 is going to be at the top of the stack, so we pop it, visit 4, and then push 5 to the stack. 5's at the top of the stack now, so we visit it, then we pop 5, we fully visited this path, and then we return to the stack. The final remaining node is 6, we pop that, visit that, and finally we're done. So when we perform depth first search, we visit down all the paths before going to the neighbors. So the way we've constructed this is if we do depth first search correctly, it starts at 0, then should print 1, 2, 3, finish that path, then visit 4, 5, finish that path, and then finally it'll print 6. So it should print all these nodes in order from 0 to 6 by the way we've constructed it. And now let's run the test for our depth first search. And there we have it. We implemented depth first search iteratively, and we walked through all the nodes going down the paths first instead of going wide first. We use a stack to store our nodes because this will ensure we've always accessed the most recently added node that keeps us following a path to its end. We use a set to track the visited nodes, and then for a node's edges, we add all its neighbors to the stack. So now I hope you have a deeper understanding of depth first search and are ready to apply it in your coding interviews. Thanks, and I'll see you in the next lesson.